Hello, I'm JW. This time I've got some fuses to look at, and these are supposed to be BS1362 fuses, but they're not, and we'll have a look at them in a moment to see why that is. Now, these were sent in by Chris, and these were really from a thing on Twitter where there was a number of pictures put up of where these fuses actually came from and what they'd been used for, and you can find a link to that in the description to this video. Now, they're supposed to be 13 amp according to the printing on them, but whether that's the case or not we'll find out later, because we're going to take these outside and shove some current through, see how much it takes before they actually fail. But before that, we'll just have a closer look at them and see how they compare to fuses which do comply with the standard, and unfortunately, as we'll see in a minute, they definitely don't. So here we have the three fuses, and so these are supposed to be BS1362, as it's rather shoddily printed on there. But these are rather poor examples, and first problem we've got is the fact that these are printed in red ink and they're marked 13 amps. Now the whole point of these is that the 13 amp ones should be marked in brown and the 3 amp ones should be marked in red, and other values including 5 should be printed in black. So red for 3 amps and it says 13, so clearly that's not good either. And so the general quality of the printing is pretty mediocre. And we can also see that the brand name on these is apparently Star, whatever that is. And as we turn it around there, you see it's a fairly mediocre example, and they're all pretty much the same in that regard. Now, in terms of the end cap, there's another problem here, because you can see there that we've got the wire, which is presumably the fuse element, goes through the middle. It's basically just sort of bent around the end and then over the top, and then this cap has been shoved over, and the other end's the same. You can see it there, that sort of indent in the metal there. And the problem with that, of course, is it's now made the end cap being misshapen. And the second problem is that on these, the wire is supposed to be in the centre of the tube here, which is supposed to be ceramic, and it's supposed to be then actually permanently welded to the centre on the end, and clearly in this case it's just been folded over and shoved the end cap over, so certainly rather misshapen and horrible. Now, in terms of general dimensions, here we've got an actual proper 13 amp fuse. This is a Bussmann one, and you can see it's printed in the proper brown there, and notably on these the end caps have that dimple in the end, which is where the actual fuse element or the wire is attached, and we'll see it does not fold around the end and make a horrible indent in the outside. But in terms of physical dimensions, we'll see that the Phaco ones are noticeably shorter in the length there by a certain amount, so they're the wrong size. And if you place them end to end, it may not be as apparent, but they're actually not the correct diameter either. So you can see there it's actually smaller, so smaller in both dimensions, and of course it doesn't comply with the standard either, because these are designed to fit into the specific sized fuse holder. Now, the size they're supposed to be, I'll just turn this thing on, they're supposed to be 1 inch in length and 1/4 of an inch in diameter, or more likely the metric equivalent now, which is going to be 25.4 in the length there, millimetres, and 6.35 for 1/4 of an inch there. So let's just measure this decent fuse here, this Bussmann example. So if we go for the length there, we'll see that it's pretty much bang on the inch there, just 1.011 or 115. And of course there are some tolerances on these things, and if you go for the diameter of the end cap there, again just fractionally over there, so 0.2525. So again, not a particular difficulty with that. But if we try these ones, again we'll just go for the length there. So as you see there, it's significantly short at 0.964. In fact, depending on how you get it, it might be slightly less than that. So yeah, 959 if we do it there, because the end caps aren't actually level. And if we do the diameter, even if we go over the diameter where the wire is, that's not quite there, 0.247. And if we rotate it, so it's got the narrow bit, well, again 0.235, so again that's completely useless. And for metric purposes, obviously 5.96 is not 635, and in terms of length it should be 25.4, well 24.4, so it's a millimetre short. And it might not seem like a huge difference, but the point is that these things are supposed to be made to a specification, and these obviously have not been. Now, something you may not have thought of is that a fuse by its very nature, it's going to have a certain amount of resistance, because inside here there's a very thin wire, certainly relative to the circuit wiring, which is designed to overheat and melt in the case of the current being too high. So we'll just to measure some of these and see what kind of values we get. Now, they're not all going to be exactly the same, because these are obviously fairly grubby and been in the drawer for a long time, but I should get some general idea of the sort of area that we're actually looking at. So I've cleaned the end caps a bit anyway, so we'll just place them onto the terminals here and see what we get. Now this reads in milliohms directly. I'm on the lowest scale, which is the 40 milliohms one, so let's see what we get with this one. So getting a region of sort of 5.5 milliohms there, so pretty small as you'd really expect. Let's try the next one. Yeah, again it's sort of 5.3 there, so fairly similar. And of course you would expect them to be similar, because they all should be made to the same specification. Yeah, sort of 5.7 on that one. Yeah, so about 5.5 there, so that may be slightly less. And then this one, say 5.5, 5.6, so all around the 5 milliohm sort of area. Now what about a 3 amp fuse? So we've got some here, these are SEM branded, but again that's a reasonably made one, it's got the correct characteristics or whatever. So let's see what we've got on this one. Now think about it, a 3 amp fuse should have a higher resistance, because the wire inside, of course, ought to be considerably thinner. So if this is going to fail, obviously at a lower current than the 13 amp version we had there. So we should expect to see a higher resistance, as the obviously wire inside is going to have a smaller cross-sectional area. So we clamp on there, and we can see it's not actually on the scale for this. So let's change up to the 400 scale. So 3 amp fuse there is actually around 51 milliohms, or in the general area of. Let's just try the next one, see if it's similar. Yep, so again around that 50 milliohms mark, and then just try the third one here as well. Got a whole box of these. So again, that's around the sort of 50 milliohms, or say 48 in that particular case. So resistance to that quite a lot higher, but then say you would expect that, because the wire inside, of course, is going to be a thinner size. So then what about our Dodgy Brothers fuses here, which of course supposed to be 13, so you'd expect them to be similar to the 13 that we had previously. So let's see what we've got. Now, do we go onto this where the wire is protruding? Well, we can't really, because they're not actually matching. So just mash onto the contacts and see what we get. So still on that 40 or 400 milliamp scale. So we're actually getting, it seems a bit inconsistent, as we press harder it seems to go up, but we're getting a region of 54, or say around 50 milliohms, which is about the same as we had for the 3 amp fuse before. That's certainly not what you want to see. It's a 13 amp job. No, this one's completely different. That's only around 16 or 15, which again isn't very consistent. And let's try this third example here. Okay, that's around 27. So they're all totally inconsistent with each other. So yeah, it's completely inconsistent in their value, and they seem to be rather higher than you'd expect for a 13 amp fuse. Now that's probably going to be due to either the fact that the wire inside is too thin, but that's not actually very likely. More likely is the crappy way it's been attached to the end cap, just sort of folded round and bodged on, not actually welded to the cap. And the problem with that is, if you've got, say, 13 amps going through it, if the resistance is double, then of course the power dissipation is also going to be double. So whereas, say, a normal fuse might dissipate, say, 1 watt or something, these could easily be dissipating, say, 2 or 3 watts, and obviously that's going to lead to significant amounts of overheating. So here's the test arrangement. So I've got the fuse here in this plug. This is an old Bakelite one, so it won't be affected by heat, because some things these may get fairly hot. Wire goes in on the back, and at the front there just to apply the current. And in the side here, just wedged in with the fuse itself, is this lead which goes to the temperature monitor here. So I'll see how hot this thing gets. Currently about 25 degrees centigrade, so it's quite a warm day today. Timer here so you can see how long it's been going for. And then the current displayed here on the clamp meter, just basically measuring on the wire going through like that. And the current can be adjusted via the variac, which is out of shot at the moment. But we've seen that in a previous video, so a link to that is in the usual place for how that works. Now to start with, we've actually got in here just a normal and proper 13 amp fuse, so I'm just going to run this for a while. I'm going to run it up to the 13 amps and see what kind of temperature difference we get. That just gives us sort of a baseline for what would be normal operation, and then of course once we've done that we'll use the dodgy fuses here and see what happens with those. So let's turn on there and we'll start the timer going there. So current's about just under 1 amp there, so we'll turn it up say until we get to 13, and then we'll leave it running at that level for however long it takes to get to a moderate sort of temperature rise. Now we're just coming up to around the 2-minute mark, and we see the temperature's increased to around 72 degrees, so we're considerably hotter than the 25 or so that we started with. Our fuses in general will heat up in normal operation, so this is a proper Bussmann fuse here, and we are running it at pretty much the maximum current that it's designed for. Now for fuses, for those that don't know, a 13 amp fuse does not instantly fail as soon as the current just tips over 13, because all it is a piece of wire that's heating up. And in most cases it takes quite a lot more current to actually cause the thing to fail. Basically it's melting the element. In the case of these it's generally about 1.6 times the rated current, and in some types of fuses, particularly as old reliable jobs, it can be up to 2 times. So in this case you're probably looking at anything in sort of region up to 20 amps to cause this to fail, certainly if it was on for a long period. But certainly at 13 amps or just below here, about 12.8, this fuse should never ever fail. It should be perfectly happy just sitting there pretty much indefinitely. Now we're in about 3.5 minutes here, and we see the temperature's up to about 80 degrees, so that's going to be pretty hot. You wouldn't want to be touching that obviously, and in the case of this, that's again normal operation. And if you actually have any higher powered appliances like say electric heaters or a kettle or something, if it's been on for a certain amount of time, you'll notice that the plug itself does get warm, because that's the heat from the fuse being dissipated in there. Now just coming up to about the 10-minute mark, and you see the temperature stabilised around sort of 89, 90. It doesn't seem to be going above that particularly. Current's still around the 12.8 amps or so, so just below the 13. So we're going to stop the test here. We can say it's been on for a full 10 minutes, and so that's a reasonable baseline as to what a normal fuse will do. Now this is the same again, we've just got the dodgy fuse installed instead. It has cooled down mostly to where it started, bit 34, that's a bit above ambient where we started about 25, but nevertheless fairly cool there. So we'll do the same again, we'll just go up to about 13 amps and see where the temperature gets with this one. So power on, and we'll start the timer going, and then we'll just turn up to around the 13 amps level. So about 12.8 there, that's pretty much the same as we had previously. Notable that temperature's already up to 72, that's considerably quicker of an increase than we had before, as bearing in mind we're not even in 1 minute yet and we're already approaching sort of 75, 76 there. So anyway, we'll leave this going and then we'll see what happens. Now we're already over 90, actually 91 just there, and this is only after 1 minute 50 seconds, so that is significantly faster than the previous fuse took to get there. And although the fuse element in this is supposed to be the same rating of 13, as we saw those resistance measurements earlier, the actual resistance of it did seem to be rather variable, and that's probably due to the end caps just being shoved over and sort of holding the wire in place by friction only, which of course may well result in a poor connection. Poor connections of course are higher resistance, and higher resistance results in overheating. So temperature there, see it's already exceeded what the other fuse got to after 10 minutes, and so we're only at 2.5 minutes so far. Coming again about saying that sort of 12.8, 12.9 area, so again 13 amp fuse should never ever fail at that sort of level. But anyway, let's just leave this going for however long it takes, and we'll come back later, see where the temperature gets to and stabilises. Now just coming up to the 10 minutes now, and we see the temperature is around 109 degrees centigrade, so it hasn't actually moved there much for the last 5 minutes or so. So we'll call that the result for this one, and the current's still around that 12.8 as we've had all along. So significantly hotter than the other kind, and so it's not too surprising given those resistance measurements we had earlier. Now I'll just change this fuse to one of the other dodgy ones. The first one is here, we'll keep that to one side for the moment. Temperature's still a bit elevated because the whole thing of course has heated up. So what we'll do this time, we'll turn this on and run it up to the 13 amps we had before, and then see if the temperature goes up at a similar rate to the other one, because bearing in mind when we measured these things the actual resistance of each one seem to be rather inconsistent. And then we'll go above the 13 and keep increasing it until it actually fails, and then we'll see obviously the point at which it does actually break. Now, as I said before, the fuse factor of these, as it's called, is generally around 1.6, so a 13 amp fuse should actually fail around the 20 amps mark, 13 times 1.6 being about 20 amps. So that's what you'd expect on a normal one. Whether these do, of course, is anybody's guess, because I've got no real idea what these are like. So anyway, let's just turn on. And let's say we'll start out just going the current up to the 13 that we had before. So that's around the 13, you see we're already up to 75, so this is very, very quick in terms of temperature increase. I'm not using the timer this time particularly. Yeah, as you see again, it's going up at a considerable rate there. So let's just start increasing it above 13 and see where we get to. So now we're at 15, so that's a significant overload. And we'll keep going up, temperature's now around 90, so 16, 17.5, and the temperature's now up to 101, so already we're at the sort of the higher temperatures than the had at the 10-minute thing earlier. Let's gradually turn up there, so now in the 19.3 range. Now we should be approaching the point where a normal fuse would actually fail, say at around the 20 amp point, so just keep going and see where things get to. So now coming up to 24. Temperature now in the region of 150, and that's obviously considerably hot. That would certainly be melting all the plastic type plugs. Say this Bakelite one I've chosen particularly for this, so that it won't be damaged by the heat in the same way. So we're now to the 25 area. Now we'll just keep turning up until something gives. So we're now shoveling 30 amps through, and the temperature is now over 200. And as you can see, oh, it did actually just break there, so that seems rather high, doesn't it? And 200 degrees there, and so temperature is now falling away as you would expect. So yes, that's certainly pretty high there, and so the 30 is pretty much the maximum that it can go up to without breaking something. So that's certainly not very impressive. Now this is the third fuse, so we've got one that's broken, the first one we had which still works, and then this third one, so we'll do the same again, and I think we'll put the timer on this time. So turn on, and we'll go straight up to the 13, or near enough. So that's sort of the 12.5 or so, which it's pretty near its supposed maximum rating. And though we started at a fairly high temperature, as you can see it's still increasing quite significantly already in the region of 80, and still climbing. So I think we'll just continue increasing there, and again we'll see where we get to. So 12 there. And we'll go a bit more quickly this time to see where it gets to without sort of overheating it along the main way. So 20, 21, 22, so that's already around 25 there, 120 degrees and still rising rapidly. It's only been on for 1 minute. Now at 27 there, so that's more than double the rating of the fuse, so of course 13 there should be a double, that would be 26, so it really should have failed by now, but nevertheless it obviously hasn't. So let's leave it on 26 there for a bit and see if it does actually break at that point. Temperature still increasing, 183 there, and it's still rising fairly quickly. Now we're coming up to the 8 minutes mark and it still hasn't failed, so I'm going to turn up the current until it does, because unfortunately some of the wires we're using to actually supply this are getting pretty hot by now. So in order to avoid those being damaged, I'm just going to crank it up until it breaks, and we'll see what level it breaks at. So 25.5 there, and we'll just continue cranking the knob and see what gives. Okay, well that's up to 32, and it still hasn't broken. Temperature's now up to 300, or fractionally below. Okay, well we just surged up to about 37 there, and it did actually break eventually. But that certainly is excessive by any standards. And bearing in mind that was after it had been sitting around for 7 or 8 minutes or so at a temperature of 250 degrees Celsius, so clearly not very acceptable. And if that had been in, say, a normal plug in a kitchen or something with, say, a pile of stuff attached to it, that no doubt would have been smoking and melting and dripping on the floor by now. Now there's really two problems here with this, in that this fuse and the other dodgy one got far too hot far too quickly. So if it was on a single appliance, say like a kettle or washing machine or something, in normal use far more heat would be given off than we would expect, and therefore the plug and things would get hotter than they should, and in case those thermoplastic ones it could melt and be damaged. And the real problem with these is that if you've got a 13 amp fuse there, and then someone's plugged in, say, one of those extension leads where you can plug, say, 4 items in, as would typically occur in a kitchen that doesn't have enough outlets, you could easily have a load of, say, 26 amps or something from a selection of appliances. A worst case scenario things if someone plugged in, say, a washing machine and a tumble dryer into the same outlet, and in this case they could draw their 26 amps quite happily for 5-10 minutes or something. Temperature of the thing gets up to 250, but of course it doesn't fail, and therefore something is going to get damaged and melt, and potentially lead to a fire if it was, say, a thermoplastic one and got hot enough to catch on fire there. The other thing to consider here is that this plug is completely open on the top, so the lid isn't there. Of course with the lid that would trap the heat in, so high temperatures from the ceiling would be even higher, just the fact that the heat can't escape as easily. Now this is the third one, so I might as well bust this as well. And this is the one we had initially, so this has already been up to a fairly high temperature and then allowed to cool off. I'll just put it back in, the rig is still quite warm, so 52 at the moment. And for this one we'll just turn it up fairly quickly and then just note the point at which it fails. So power on, we'll turn on the timer as well, might as well, and then we'll just turn up and see where we get to. So 8, 9, 10, 11, that's 12, so 13, so now we're over the rating. 18, 20, so we should be into the failure zone now. 26, 27, 28, 29, 31, 32, so that was about 37 there. And we're seeing in that short time the temperature still got to around 170 plus, so again pretty excessive that would seem. And finally, just for completeness, what we've got in here is the 13 amp busman fuse, so the proper sort, and we'll do the same again, that fairly quick ramp up, and see at what point this one fails. So we use the timer again, so power on, start that going, and then we'll turn up on that one. So that's 8, 9, 10, 11, so 12, 13. Notably the temperature isn't increasing anywhere near as quickly there. So 17, 19, so 30, and it's already failed, so there we go. So didn't get exactly the figure there, but it was around the sort of 30 or just over. But notably the temperature in this case only got to around 100, considerably less than the very high temperatures we're seeing with those Phaco fuses. Now let's just see finally what kind of sand filling they have inside. Now this is the busman one, so this should have the sand filling inside, and that's in there so that if there's a high energy fault, such as a short circuit, then this will absorb the energy and avoid the thing exploding in a ball of flames. Now the faults we had here were very low energy, so of course it wouldn't have happened either way, but let's just crack into this one and see what we can find within. So there we go, and there's the sand filling inside. And we can see the remains of the fuse element there as well. Now this is a ceramic material here, sand contained there. So now let's try these Dodgy Brothers fuses, and do we really expect these to have sand inside? Well, as you can see, so there we are, it's broken away, and unsurprisingly, yeah, no sand in there whatsoever, although it does appear to be a sort of a ceramic type tube there. Here's the one we had on for a long time, and you see the printing has discoloured due to the massive amounts of heat that's being given off. So let's bust into that one. And yeah, as expected, of course, no sand there. And obviously the third one, no, it's going to be exactly the same, so no real surprises regarding that. And yeah, there it is. So once again, no sand contained within. And we can see the wire there. I mean, it may well be around the correct sort of size, but it's very difficult to tell these things from a visual examination. And even if you actually look at them under a calipers or something, it's such a thin size that it may not be entirely obvious. But there's the two examples. This is a sort of a coppery coloured thing, and the Busman one is a rather more black colour there, so not really we can judge from that in a visual way. So that's the end of those fuses, and unsurprisingly they certainly didn't perform well. Now the tripping current isn't particularly conclusive because, as I say, even the normal ones are not supposed to trip until they get into the 20 amp range, which is about 1.6 times the rated current. But as we saw there, that Phaco one ran at about 26 amps for many minutes, getting to an exceptionally high temperature. Clearly that's not supposed to happen. And the other main point there is that the increased resistance, probably of the end caps and the way the wire was just sort of crimped around under them, would have resulted in those extreme temperatures coming up far more quickly. Saw that Busman one at the end. Although it was driven up to about 30 amps, the actual temperature of it remained fairly low compared to the fake ones. And the sand filling, of course, that's there to absorb the energy in the case of a high energy fault, such as a short circuit. And if you put a short circuit on something, there's going to be many hundreds of amps, or in some cases a few thousand of amps flowing, and the sand is there to absorb the energy from that. If the sand isn't there to absorb the energy, then the energy is going to go somewhere else. And in the case of cheapo fuse like that, the fuse exploding is a fairly likely outcome, and that could also cause damage to all kinds of other stuff as well. Now we're not going to be demonstrating that because we don't have the facilities for it, but there are demonstrations of that available elsewhere. So anyway, that's the end of those fuses, and it's also the end of this video. So until next time, thanks for watching.